In the first video of this module, we discussed symbolic notation and essentially how to translate ordinary language propositions into a symbolic form. In doing so, we looked at a number of different possible operators which were used to connect simple propositions together into more complex ones. The next step in all this, in understanding propositional logic, is to understand the concept of a truth function and then look at individual truth tables for these different operators. So let's start with the idea of a truth function. Now, any simple proposition in propositional logic is said to be truth functional. We talked a little bit about this in the last video, but the basic idea is really quite straightforward. All this really means is that that proposition as an individual proposition can be understood as being either true or false. And so now we can add a little bit to this concept. When we start talking about compound or complex propositions, things get a little more complicated. The truth value of any compound proposition, expressed in terms of one or more of our logical operators, is going to be a function of the total truth value of all the components working together. So if we take, for example, the statement R and W, whatever R stands for and W stands for as simple propositions, the truth value of this claim as a whole, this conjunct, is going to be based on the truth value of all the constituent parts working together. That is, we would need to know the truth value of R, we would need to know the truth value of W, whether it's true or false, and then we need to understand what the truth value of a conjunction would be based on the truth value of those simpler parts. So let's put this in terms of an example. Take the statement, "It is raining right now and the street is wet." So we can translate this into symbolic form by just saying something like R.W. And notice the point here is if we want to know if this entire statement as a conjunct is true, in order to make such a determination, to know if this entire statement is either true or false, what I would first have to do is know the truth value of the initial simple proposition. That is, I need to figure out if it is or it is not raining right now. And then I need to know the truth value of the second simple proposition. That is, I need to determine if the street is wet or it is not wet. And then I need to understand what is logically implied by that distinct operator, a conjunct. So we might imagine that it's not actually raining outside right now, but the street is in fact actually wet. And then we are finally at a point where we can figure out, is this true or is it false? Is the entire statement true or false? And of course, that depends on what the operator implies under these specific truth conditions. Now, to understand what each individual operator implies about the truth value of a complex proposition, given different possible truth values for the simple statements, what we do is construct what is called a truth table. Now, if you recall, there are exactly 5 different logical operators, and so we have 5 different truth tables that we need to work with. These 5 different operators, if you remember, are the negation, the implication, the disjunction, the conjunction, and the equivalence or the biconditional. Now, given that the truth value of any compound proposition is determined by the truth value of its simple components, a truth table can be constructed to show every possible arrangement of truth values in every possible case for any possible operator. In short, you can think of a truth table as just asking ourselves, what does that operator imply in every possible arrangement of our truth values? So let's say we know that both of our simpler propositions are true, or we know that both of them are false, or one is true and the other is false. What would it imply in each possible arrangement of these truth values? Now, when we construct truth tables to define the total truth value of different operators, what we're going to do is substitute statements, whether they are simple or complex, with what we call statement variables. In other words, what we're going to do is find a sort of replacement for whatever it is that the original statement is, And in doing so, when constructing a truth table for our operators, we're going to start using lowercase letters. This can be a bit confusing at first, but it's important you understand what we're doing when you see a lowercase letter. A lowercase statement variable can stand in as a placeholder for any conceivable proposition, whether it is simple or compound, and it really doesn't matter how complex it might be. So let's say one of the variables is a simple statement. We'll just say A. What we want to do is simply replace that with a lowercase letter p to signify that we're just dealing with that side of the equation, whether it's a conjunct, a disjunct, or whatever. We're just going to substitute in this little p, lowercase p, as a placeholder. Or we might imagine that one of my conjuncts or disjuncts in a compound proposition is the entire statement A and B. And when constructing a truth table for that particular statement, what I'm going to do again is simply substitute for that entire statement a lowercase p or a lowercase letter as a placeholder. And no matter how complex it gets, the entire statement will simply be substituted with a lowercase variable to represent that entire thing as one side of the logical operator. And again, it really doesn't matter how complicated it is. If this represents one side of my operator, I'm just going to stick in a lowercase variable in order to construct a truth table. So again, P can represent pretty much anything. And when you see a lowercase letter, make sure you understand that this does not represent a simple proposition like capital letters do. This represents any conceivable variable in a particular operator on a truth table. So let's see how this works and see if we can make some sense of this. And we'll start with one of the easier ones to deal with, the negation. So let's use the letter P to represent any statement, no matter how complex or simple it might be. So P can represent literally any proposition whatsoever. And then our question is, what happens when you negate it? Well, the first step is to recognize that there really are only two possible truth values for P by itself before it's negated. P can either be true or it can be false, and there really is no other option. And again, no matter what you're talking about, no matter how complex the statement is, in the end, it's going to be either true or it's false. So when we construct a truth table, the first thing to do is determine all of the possible truth values of that statement variable. In this case, we're using the lowercase letter p. And we only have two, true or false. And then we just need to ask, if I know that p is true, but I negate the claim, what truth value should that produce? And of course, notice if p is a true statement, and I say it is not true, then I must be wrong. I've made a false statement. And if P is a false statement, and I say it is not the case, then what I'm going to assert is that it is true. So basically, a negation is really simple. A negation just takes whatever truth value you have with the original proposition, and then it just does the opposite to it. If it's true and you negate it, it becomes false. If it's false and you negate it, it becomes a true proposition. So this basically represents my total truth value of a negation. And again, the basic idea is it just does the opposite to whatever we're talking about. So let's put this in terms of a simple example. Take the statement, it is not the case that Paris is the capital of Germany. Well, notice the symbolic formulation of this would be something like C negated by a tilde, so not C. And of course, notice the statement, Paris is the capital of Germany, is a false statement, but I have negated it. So the total statement with the negation makes this a true pronouncement. If I say Paris is the capital of Germany, that's a false statement. To say Paris is not the capital of Germany makes it a true statement. And we can just run to our truth table here to see this result. Notice the p value, in this case is just represented by the letter C, is false, and I negate it so it becomes a true statement. So what about a conjunction? Things will get a little bit more complicated once we start in with the remainder of our operators. Now remember, a conjunction is just an and kind of claim, and it will be surrounded by two different conjuncts. So that means we must have two different terms, and we want to give them a lowercase variable to identify them. And again, P here and Q can represent literally anything that sits on each side of that dot of a conjunction. So each of these represents a conjunct, whether it is a simple statement or a complex one. Now, in terms of the possible truth values for P and Q, whatever they stand for, one possible arrangement, of course, is that both P and Q might be true. P might be true, but Q could be false. P might be false and Q could be true, or both of these might end up being false. And notice this arrangement here gives us every possible truth value that could exist in terms of a relationship between P and Q. They both might be true, they both might be false, one might be false and the other true, and the other way around. So if we want to set up our truth table, we want to basically transfer over all of these possible truth values under each of our terms, and then separate them by a simple dot. So it turns out with a conjunction that a conjunction is true only under the condition that both of the conjuncts are also true statements. So the entire conjunction, the statement as a whole, can be true only if both P and Q, or whatever those stand for, both P and Q are true statements. Any other possible arrangement will be a false statement. So if I have a conjunct where one of my statements is true and one is false, then it must be a false statement as a whole, or if both of them are false, then it's a false statement as a whole. So keep in mind with a conjunct, the only time a conjunction is in fact a true statement as a whole is if both pieces, both of my conjuncts are actually true statements. So once we've constructed our truth table, where we have every possible arrangement of truth values between P and Q here, what we find basically is, again, the only time we get a true statement is if both are true, everything else must be false. So let's look at an example of a conjunction, and then we can use our knowledge of the truth of these various statements to determine the truth of the statement as a whole by simply turning to our truth table. So the statement says Texas is a state in Canada, and Canada is a member of NATO. Formally stated, it would just be something like T.N. And of course, notice the first statement, T, Texas is a state in Canada, is clearly a false statement. The second one, Canada is a member of NATO, is a true statement. And so we can go to our truth table to determine the truth value of this statement as a whole. And of course, this conjunction then is what we're working with. If I have one term that's false and the other that's true, we know this has to be a false statement as a whole. So this conjunction, the entire statement, must be false. And again, you can see this by just running through the truth table. What I have is the first term, T, is false. The second term, N, is true. And under those conditions, where one is false but the other is true, in a conjunction, it must be a false statement. So our truth table is capable of sorting out every possible arrangement for a conjunction when it's true and when it's false. And in the case we just saw, it must be false. How about another example? This one says Miles Davis played the trumpet and John Coltrane played the saxophone. Symbolically stated, this would just be something like T.S, both capital, with my simple terms, T representing Miles Davis played the trumpet, S representing John Coltrane played the saxophone. And of course, both of those statements are true. Miles Davis did indeed play the trumpet, and John Coltrane did indeed play the saxophone. So I have two different terms here that are true put together by way of a conjunct. And of course, when you have a conjunction where both of the terms are true, we know this is true. And we can go to our truth table to determine this. And again, what we find is the first are two terms, T and S, are both true statements, and that is the only time when a conjunction will be true. And this is basically how you use a truth table to determine the truth value of statements when you already know the truth value of those terms. So let's take a look at a disjunction, that is, at our either or claims, and see how these work. So any disjunctive statement, of course, is going to have exactly two terms, both of which will be disjuncts. And again, we can signify this or represent this on a truth table by two lowercase letters, in this case, P and Q. And again, P and Q can stand for anything, either simple or compound. And just like we saw with conjunction, these two variables can give us only four possible arrangements of truth values. That is, P and Q might both be true, P might be true and Q might be false, P might be false and Q might be true, or they might both be false. So we can construct a truth table by simply sticking in these various possible truth values under each of these two terms, P and Q, and then we just need to see, what does a disjunct tell us? Well, it turns out that a disjunctive statement only needs one of its variables to be true in order for it to be true. So in the first three options, where P and Q are true, where P is true but Q is false, or P is false but Q is true, this will render a disjunctive statement as a true proposition. The only time a disjunctive statement is false is if both of my disjuncts are false claims. So if you look at this, what you find is a disjunctive statement is true in every possible case except where both of my disjuncts are false. This is basically the exact opposite of a conjunction. A conjunction is only true if they're both true. A disjunction is only false when they're both false. Now, if you remember, disjunctive statements can be a bit ambiguous, and we can talk about a disjunctive claim in both a strong and a weak form. And so we need to deal with this problem in terms of our truth tables as well. Remember, an inclusive disjunctive statement is one that means and or, and what this implies basically is one or both of these propositions can indeed be true. So an example of this might be something like either it is cold or it is raining. We saw this example before. And notice if I say either it's cold or raining, this could very plausibly imply that it is both cold and raining at the same time, and that disjunctive claim does not render that an impossibility. An exclusive disjunctive claim, on the other hand, is the kind where if one is true, the other must be false. The terms cannot both be true at the same time, and they cannot both be false at the same time. So this is something like either it's living or it's dead. Either the door is open or the door is closed, or countless others, where essentially if one of these possibilities is true, the other one simply couldn't be true. And of course, this changes the truth table a little bit. Because if you recall, what we're actually saying with an exclusive is essentially an inclusive claim. It's either P or it's Q, and then we add to this a conjunction. And it is not the case that both P and Q are true at the same time. So technically speaking, when you deal with an exclusive claim, you should translate it just as we see here, P or Q and not P and Q. But there is a way to get around this using our truth tables. And the first step is to recognize that when we talk about a disjunctive claim, the default assumption will be that we're talking about an inclusive disjunction. That is an and or. And when you have an inclusive disjunction, the arrangement of the truth value is exactly what we saw, which is it's always true unless both of my disjuncts are false. What happens with an exclusive disjunction is that the first possibility changes. That is, if they're both true or they're both false, then it becomes a false statement. Because remember, an exclusive tells us they can't both be true at the same time, and they can't both be false at the same time. So if I assert that they're both false, it must be false. Or if I assert that they're both true, it must be a false statement. Now, instead of this complicated P or Q and not P and Q, there's a very easy cheat here that I'm showing you in red. Notice what we can do is simply change that to an F and then put a little tiny X above the disjunctive wedge to remind ourselves that we're dealing with that problem. So if you know you have a disjunction, what we can do is use the exclusive truth table. So it's false, true, true, false instead of true, 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 false. And then you just remind yourself by putting an X there. Now, if that's confusing, you can just always go right back to the original requirement, which is to use this complicated translation of P or Q and not P and Q. So let's take a look at an example of a disjunctive statement, and then using our knowledge of the various simple propositions, let's figure out if this is a true or a false statement as a whole. So the statement says either Plato wrote the Republic or Beethoven wrote the Magic Flute. So the symbolic translation of this would just be capital P, wedge, capital B. And of course, notice the P stands for Plato wrote the Republic, which is a true statement. And the B stands for Beethoven wrote the Magic Flute, which is clearly false. And of course, a disjunctive statement, remember, only requires that I have at least one of my terms as a true statement in order for the entire disjunctive statement to be true. And since the first one is true, we know that this must be a true statement. And we can see this by running to our truth table, where we take the first term as true and the second one is false. On that particular line, what we discover is that that disjunctive statement as a whole must be a true statement. So let's look at another example. This one says, unless water freezes at 52 degrees Fahrenheit, every lake on this continent is covered in ice. Now remember that an unless claim generally translates into either or. So this is basically telling us either water freezes at 52 degrees Fahrenheit or every lake on this continent is covered in ice. And so the translation would just be F wedge I. And of course, both of these statements are clearly false. Water does not freeze at 52 degrees Fahrenheit, and it is also false to claim that every lake on the continent is covered in ice. So we have a disjunctive claim where both terms are false. And of course, when you have an either or claim where everything in there is false, the entire statement must be false as well. And again, we can run to our truth table and just go look and see what those variables are. Notice if both of my disjuncts represented by P and Q on the truth table are false, then that disjunct, what we find in terms of the truth value for that wedge, must also be false. So let's look at the next operator, the implication. That is our conditional statements, the if-then claims. Now, of course, any conditional statement will have exactly two terms to it, both an antecedent and a consequent, which we can represent on our truth table with these lowercase variables P and Q. Now, whatever P and Q stand for, they can be simple terms or they can be compound ones, but there'll be exactly two different possible terms in the statement as a whole. And of course, if there are exactly two terms, this means that there are exactly four possible truth relationships between those two terms. They might both be true, they might both be false, or one is true and the other is false. And so we get the same basic arrangement we see with the conjunction and the disjunction, where P and Q are true, P is true but Q is false, P is false but Q is true, and P and Q are both false. And so to set up our truth table, we simply want to plug in the truth values of each of these terms, P and Q, my antecedent and consequent, in order, where both are true and so on. And then we just want to run through all of the possible truth values. And it turns out that in a conditional statement will be a true proposition under any possible arrangement except where the antecedent is true, but the consequent is false. So if it's both true, then it's a true statement. If the antecedent is false, but the consequent is true, then it's a true statement. And if they're both false, it would still be a true statement. Now, unlike with a disjunctive statement or a conjunction, this isn't so obvious. So we might stop and ask ourselves why. Why would it be that under only this one condition, where the antecedent is true but the consequent is false, that this would render it a false statement? And we might even want to know why, if both are false or one is false, the antecedent is false, that it would render it true. So to make this clear, we can start by just imagining that you had a professor who told you, if you get an A on the final exam, then you will get an A for the entire semester or quarter. Now, ask yourself, under what conditions could you say that your teacher lied to you? So let's say that you did indeed get an A on the final exam, and then you did get an A for the course. Well, you would rather naturally be inclined to say that this initial conditional statement must have been true and that your professor didn't lie to you. But of course, if you did get an A on the final exam, but you did not get an A for the course, then you would have good grounds or reasons to think that you were lied to, or that this original conditional statement was in fact a false statement. So what about the other two, where the original antecedent is a false statement and it produces either a true consequent or a false consequent? So let's take a look at the first of these two possible examples. Let's say that you did not get an A on the final exam, but you nonetheless ended up with an A in the course. Would we really want to say that your professor lied to you? Well, not really, because it might be that you'll just get an A for the course anyway. You had an A whether you took the exam or not, and if you got an A, you would indeed still get an A in the course. And of course, if you fail to get an A on the final exam and you don't get an A in the class, then everything is exactly as you expected it to be based on the original proposition. And so once again, you have no good reason to think that your professor lied to you. The only time that you would have good grounds to think your professor lied is if you did indeed get the A, but you didn't get the A in the course. So here's what you find out about a conditional statement. Again, a conditional statement is true under every possible arrangement of our truth values of the antecedent and the consequent, unless the antecedent is true, but the consequence ends up being false. So once again, let's take a look at an example of a conditional statement, and then using our knowledge of the truth of the antecedent and the consequent, we can determine if this is a true or false conditional statement. So the conditional statement says, if Paris is in France, then Paris is in Europe. And translated into symbolic form, we would just get F horseshoe E, where F represents Paris is in France, and E represents the claim Paris is in Europe. Well, of course, both of these propositions are true. It is true that Paris is in fact in France, and it's also true that Paris is in Europe. And so what does that tell us? Well, a conditional statement where both the antecedent and the consequent are true is going to be a true conditional statement. And we can see this by running to our truth table, where we just look at both the terms P and Q here, our antecedent and consequent, as both true. And what we find is that the conditional statement itself must be rendered true based on this basic arrangement. Let's look at another example. This one says, if George Washington was decapitated, then he is dead. Now translated into symbolic form, it would look something like this, W horseshoe D, and then we just have to figure out, was W true or false, and is D true or false? And of course, notice George Washington was not decapitated, but he is in fact dead. So the arrangement we end up with is the antecedent is false, but the consequent is true. And so what do we know? Well, with a conditional statement, under these conditions, this is in fact a true statement. So we just have to run to our truth table and look for the arrangement where the antecedent is false, but the consequent is true, and we discover it's true. And of course, notice if you are decapitated, you're going to be dead. It just turns out that George Washington was dead anyway. So we have our last operator, the equivalence, or what is called the biconditional, represented by the try bar. Now, if you remember, the try bar is basically telling us if and only if. So logically speaking, the claim P if and only if Q is identical to saying if P is true, then Q is true, and if Q is true, then P is true. And of course, in any equivalence statement or biconditional statement, what we find is we'll have exactly two terms, and we can represent these on a truth table with a lowercase p and a q. Whatever P and Q stand for, whether simple or complex, it turns out that there are only four possible truth arrangements of those terms. That is, P and Q could both be true, P could be true, Q could be false, P could be false, Q could be true, or P and Q could both be false. And so we want to simply lay them out on our truth table under their corresponding terms, separated by this tri-bar to show the conditional relationship. And then we just need to see what happens. Well, it turns out that this is a true kind of statement only under the condition where both of the terms match their truth value. If P and Q are both true, then this is a true statement. And if P and Q are both false, then it's also a true statement. These are rendered false when they don't match. When I have one that's true and the other is false, or vice versa, this cannot be a true statement. So with a biconditional, what we find is it's true when the terms match their truth value. It's false when they're opposite of each other. And so we have a finished product here of our truth table where we get true, false, false, true. You can actually think of this as kind of the opposite of an exclusive disjunctive statement. But if that's confusing, you might just memorize each of these truth tables. So let's look at an example to see how this would work, where we have a biconditional statement or an if and only if claim, and then we can use our knowledge of the truth of the simpler statements in order to determine if the statement as a whole is true or false. And this one says, zombies are real if and only if dead bodies can be reanimated. So a symbolic representation of this would just have capital Z, tri-bar, capital R, where Z represents zombies are real, and R represents dead bodies can be reanimated. And of course, neither of these claims are true. Zombies are not real, and dead bodies cannot be reanimated. If they could, zombies would be real. And of course, since both of these claims are false, in a biconditional, that means that this must be a true statement as a whole. Right? So remember, with a biconditional, if my truth values match, it makes it a true statement. When they don't match, it makes it a false statement. And again, we can just run to our truth table, go find the relationship we're looking for, where both P and Q, whatever they stand for, in this case Z and R, are false, and then just go see what the truth value is. Turns out that this would have to be a true statement. So let's run through the results of all of this. If we start with our negation, remember the basic idea of a negation is whatever truth value the original term has, when it's negated, it gives you the opposite. So if P is a true claim, then the negation of it must be false. If P is a false claim, then the negation of it must be true. The basic truth table for any conjunction is going to be one where it is true only if both of my conjuncts, in this case P and Q and whatever they stand for, are true claims. In every other possible arrangement, a conjunction must be false. So again, a conjunction is true only if both sides are true. A disjunctive statement, on the other hand, is pretty much exactly the opposite. What you find with a disjunctive statement is that it will be true in every possible situation except where both of my disjuncts are false. If both of them are false, then it must be a false statement. Every other possible arrangement renders it true. An implication or a conditional statement, on the other hand, is false only under one possible arrangement, where the antecedent is true, but the consequent is false. Every other possible arrangement is going to be true. And finally, the equivalence or a biconditional, that is an if and only if claim, is true whenever the truth values of the two terms match. It's false when they are opposite of one another. Now, these 5 truth tables are going to be extremely important all the way through this section of the course. You must know these. I would strongly encourage you to sit down and memorize them. And if you don't understand these things, you really need to make sure you do. Talk to me sooner rather than later. And that's pretty much an end to this module. Both of the videos are going to offer you incredibly important foundational ideas that we're going to build on all the way through the rest of this particular section of the course. So I'd strongly encourage you to get very, very comfortable with translating from ordinary language into symbolic notation and get very comfortable with the logical implications or the truth values of your various operators. I promise you, you will want to memorize all of your truth tables and get very comfortable with using them.